Hello everyone. My name is Jean, and I'm from Cosylab. And today I would like to talk to you about the lessons that we have learned while building a control unit for a quantum gyroscope. So, really taking this thing from the lab environment and deploying it in the real environment. So, before we jump into this, I would like to first tell you what I'm going to be talking about. So, to give you a bit of a rundown, since we are an engineering company, we work a lot with startups and research labs, and we see challenges that they face when taking this leap to industry. So first I'm going to talk about that, what kind of challenges we see. Then I'm going to introduce you to Cosylab, who we are, what we do, and how we help our customers. And then we're going to dive into the project. So the GIRAFFE project is a consortium that we have collaborated on, where we did this quantum gyroscope. And first, we're going to have like a bit of an overview of why quantum gyroscopes are important and how they're driving innovation, diving into the project itself, and then what we built to make it a pre-commercial product. Lastly, finishing on the key lessons that we have learned, and also I will be finishing with some closing remarks and who you can meet at our booth. So, without further ado, since we work with researchers and startups, we see what kind of challenges they face when taking this leap to industry. So, in order to scale their systems, we've seen that they use off-the-shelf components, which is great for the lab environment, but not so much suited for scale since they can be quite expensive and also are not tailored to your end use case. With this in mind, this can now threaten your funding milestone or your technical milestone that is really critical for the financing of the R&D to move along this technology and really advance it. So the alternatives that we have seen that companies and startups use is that they talk to consultants, which is great, but can be a bit limited on the execution side, that they also use partial service providers, that if you calculate in the time that you have to manage them can also be very nice. And that you build an internal team around it to really help make that leap to industry. This can be a little bit fragmented or risky if you have to learn new things with a deadline hanging over your head. So these risks that I have just mentioned, we can take over here at Cosylab, since we are an engineering company focusing on custom control system development for complex machines, and can really take over the responsibility of delivering an end-to-end solution. So we've been around for more than 25 years, have more than 200 engineers, and work in various industries. So with particle accelerators, with fusion, with lithography systems, and also quantum systems. And with a wide variety of competences that we have, we also see that perhaps for quantum, the most interesting would be custom FPGA development, custom control system development, or custom electronics development, and process-driven delivery. So really knowing the whole processes that you have to take in order to commercialize your product, doing the testing, the certification, and really everything in between. So we work a lot on grants and also in consortiums, which also this project was about. And before I dive into what we did at the consortium, let me just give you a brief overview of how quantum gyroscopes are driving innovation. So the current MEMS gyros, the micromechanical systems that you find in your phone or in your car, these gyroscopes are really hitting their limits now for the next generation of autonomous flight and driving. So they have drift, meaning that they lose accuracy over time, and this is just not reliable enough for these next generation of autonomous vehicles, which would require also navigation in areas where there is no external connections. So where there is no GPS signal, where the GPS signal can also be jammed or it can be weak, and these are risks that the new autonomous vehicles just cannot take. For this, GPS-free navigation has to be made, and the quantum gyroscopes here are the answer. Really, you can think of it as a drone with a quantum gyroscope could navigate a pitch-black cave for hours, knowing exactly where it is positioned in space, and know exactly where it is without any kind of GPS connection. So this is very valuable, and exactly in those industries that you see right there. So we have the space, automation, maritime industry, aviation. All of these industries can be impacted, and the current market for quantum sensing is around 800 million right now, and expected to grow to 1.4 billion in the next 5 years. So this means that also the technology developed in this consortium was extremely relevant. So let's dive into the consortium, into the project, and let me introduce you to GIRAFFE. So GIRAFFE, meaning gyroscopes for autonomous flight, driving and flight assistance. So this consortium was led by Silicon Austria Labs, and with also other partners like Infineon, University of Stuttgart, Beyond Gravity, 4A Systems, and AVL. And really the goal of this consortium was to take this NV gyroscope technology and prove its applicability in the field, really taking it from the lab and demonstrate proof of industrial applicability. So for those of you, perhaps, who don't know what the NV before this gyroscope is, or why is there a diamond here on my slide, let me just quickly explain what are NV centers. So NV centers are vacancies inside a diamond, an atom vacancy that has been replaced with a nitrogen atom. This pair can exhibit quantum properties, and by changing its position in space, these quantum properties change. So by taking advantage of this, we can make a quantum gyroscope, and really by shining a laser on that NV center, and then after its rotation, measuring how we are positioned, measuring the phase shift of the light, we really know how we are positioned in space. And this measurement has been done in the lab multiple times. But let's look at what we did at Cosylab to really make this suitable for deployment, and how we developed the embedded control electronics. So nobody could say it better of what we did than our lead quantum architect on this project, Jörne. And I'm going to explain the control system in 3 layers of what we did, what made it suitable for deployment, and then later on I'm going to compare it to the sensitivity that this gyroscope has. So Jörne says here that we have developed the firmware and the software for this gyroscope to control this NV center, and we did this while using a special kind of FPGA, an RFSoC that has the RF already integrated onto the chip. So this was the first layer of the control system, really the signal generation, the voice of the system that is talking to the diamond. With the RF being integrated, we can generate very high bandwidths and up to 3.5 gigahertz, really giving us also that high fidelity needed for running our quantum protocols. In the second layer, we would have the real-time data processing layer. With this, we have to make sense of the information coming back from the diamond on the fly. So really doing real-time connection and knowing how we are positioned in space instantly. The last layer would then be the timing and the coordination layer, which you can think as the conductor of the entire system, really making sure that every note is played at the same time that is needed to the nanosecond precision, so that everything works all the time, and the system runs deterministically, so it is robust and can be deployed. So really what we did was we embedded these three critical functions onto the board, and by embedding this, it was able to be deployed, proven that it can be deployed in the field, and has a 2,000 times improvement in accuracy compared to normal gyroscopes. So the MEMS gyros that I mentioned in the beginning have a drift of around 20 kilometers over 10 minutes. So this quantum gyroscope has a drift of maybe 10 to 100 meters. So this is almost a 2,000 times improvement into in accuracy that can be used in autonomous flight or driving. So the lessons really that we have learned while building this quantum gyroscope was the control unit for this quantum gyroscope was, I think, best described also by one of our partners. So Jaka Pribošek here from Silicon Austria Labs, what he said that they liked very much about the platform was that it enabled them to run those high-fidelity nuclear spin readouts without the need of an external computer, because everything was embedded. So really the first lesson here would be, because everything was embedded, like the three critical functions of the system were embedded, that we really played into less connections, having fewer moving parts, and therefore less things can break, making the system more robust. Secondly, because every critical function was embedded, it was also helped play into the miniaturization aspect of the system, making it smaller and more suitable for deployment. And lastly, setting up the architecture for industrialization from the start really helped reduce that integration risk and the need for any redesigns later on. So these were really the key lessons that we have learned while working on this control unit for this gyroscope. And if there is one key message that I want you to take away here today, is that at Cosylab, we don't provide any products or so. We rather provide a tailored service, specifically tailored to your end use case, that can help you advance your technology from the lab environment into the field to be commercialized. So if you're ready to go from it runs on my laptop to we are product ready, please come visit it at our booth. Booth number 5, we have seen that we work best with quantum startups, somewhere from A to C funding rounds, and also labs and institutions who are developing their proof of concept or their minimal viable products. Not so much for scale-ups that already have their existing products, but either way, we would love to talk to you. So please come stop by our booth. It's booth number 5. There you can meet Jerne, our lead quantum architect, me, Tanya, and our quantum cat. It's a really fun origami game that you can try with a very cute story behind it. So yeah, thank you everybody for listening. My name is Jean. I'm from Cosylab. Thank you.